Let's close out section 3.2 with one more topic. That is piecewise-defined functions. A function that is defined with different equations on different parts of its domain is called a piecewise-defined function. That is, we define the function in pieces. Believe it or not, absolute value can be defined as a piecewise defined function. Now, your calculator doesn't think about absolute value in the same way that you as a human think about absolute value. Previously, we discussed that absolute value represents the distance between any point on the number line and the origin. Because distance can only be positive, we know that absolute value always comes out to be a positive number. But a calculator doesn't understand all that. So how do we program the absolute value function in our calculator? We do it as a piecewise defined function. That is, f of x equals two possibilities, x if x is greater than or equal to 0, or negative x if x is less than 0. So I have two different rules for the function, and the rule that I use depends on the location of the input in the domain. For example, if we want to find the absolute value of 3, notice the input there, 3, fits this description. 3 is greater than or equal to 0. So here's the rule that I use to find the absolute value of 3. I just plug 3 in for x. Therefore, the absolute value of 3 is 3. But if we find the absolute value of negative 3, notice the input here is negative, so that fits this description. Negative 3 is less than 0. Therefore, we use this part of the function rule. We have negative x, or the opposite of our input. Negative 3 gives us positive 3. That's what is in the programming of your calculator behind that absolute value function. Let's consider enrichment example 10. For those of you going on to Calculus 1, you'll develop the concept of piecewise defined function in more complexity. So here's a sneak peek of what you might encounter. Consider the piecewise defined function below. Find the requested function values and then graph f of x. So we have the function f of x given in three pieces. Negative 3x if the input x is less than negative 1, 0 if x is equal to negative 1, and x squared minus 4 if x is greater than negative 1. So let's try our first evaluation. We want to calculate f of negative 2. So we have to figure out which rule to use. Negative 2 is less than negative 1. Therefore, I'm going to use this rule. We'll plug negative 2 in for x to obtain negative 3 times negative 2, which gives us positive 6. On our next one, we want to calculate f of negative 1. Again, we have to figure out which part of the domain it fits in. Well, x equals negative 1 precisely fits this restriction right here. So we're going to use this rule. Notice there's nowhere to put the input. This is just a constant function. So the input negative 1 yields the output 0. And our last one, we want to calculate f of 0. Clearly 0 is greater than negative 1. So we'll plug 0 in using this rule. That is, we get 0 squared minus 4, which gives us negative 4. Now, we want to attempt to graph this function. At this point, we have three ordered pairs on the function. We have ordered pair negative 2, 6. So we can go ahead and plot that on the graph. It's a little off the graph. That's okay. We have ordered pair negative 1, 0. We'll plot that here. And finally, we have ordered pair 0, negative 4. So that's a start, but what does the rest of the graph look like? Well, to figure that out, we're going to treat this like it's three separate functions. I'm going to start with the graph of y equals negative 3x. This is a transformation of the identity function y equals x. If we think about the graph of y equals x, negative 1 times x reflects the graph across the x-axis, and then we're going to stretch it by a factor of 3. So without going into too much detail here, the entire graph of y equals 3x looks something like this. I'm just going to sketch it in with a dashed line. Okay, that's the entire graph y equals negative 3x. But we only want the piece of this line with x values less than negative 1. So here's the line, x equals negative 1. So I just want the piece of this graph left of -1. So I'm going to take my eraser and come in here and remove everything to the right of -1 and just include the piece of this graph with x values less than -1. That's this side of the graph. Also, because we have a strict inequality there, I'm going to use an open circle at the endpoint. Okay, let me remove my sketch lines here. I'll just replot those other two. Now let's look at the next piece. The next piece says when x is -1, y is equal to 0. Well, that's only a single point, and we already have that plotted over here. So all that remains is to graph this third line. Let's consider the graph of y equals x squared minus 4. Now, our parent function here is y equals x squared, but because of our minus 4, we're going to move that down the y-axis by 4 units. So notice our graph would look something like this. If we think about transformations, I'm just going to sketch this in. But I only want the piece of that parabola with x values greater than -1. So this is the vertical line x equals -1, and I just want the piece of the graph with x values greater than -1. Because we have a strict inequality there, we're going to use an open circle at the endpoint, and then I'm going to remove the rest of this that I used to sketch the graph. So that's what the piecewise-defined function looks like. It's a broken function, discontinuous. It's got different pieces of different functions. But again, you'll develop that more in Calc 1.